thing I'm doing. Actually, it was about half of my PhD, not all of it, but it was the most published part of my PhD. So some of the work, so for example, the high contrast imaging work was a year of my PhD, never to be published, and I'm reviving it again now.
Oh, that's nice.
And the pulsar astronomy also has the same. So the half of my PhD that did get published is the addition and subtraction.
Very, very nice. Okay, people are connecting.
Can you explain me a little bit about this forum?
About, sorry, I didn't understand.
Like general astronomers, general physicists.
Okay, we are, yes, we are, LINEA is a laboratory that actually serves data and resources to different astronomy groups. So here we have cosmologists working, and also from different institutions. So we have solar system science, we have Milky Way science, galaxy science, we have cosmology science, extragalactic science. So there are different fields, and the audience is mainly composed by astronomers, but we also have in the audience people from IT people that work with us, that helps us develop software. Actually, they develop astronomy software intended to analyze astronomy data, like products for the dark energy survey, a science portal that they need to analyze data, and now and many other resources. So basically, the audience is astronomers, astronomy students, and IT personnel. Well, I think we should start because we are already 5 minutes.
Okay.
Over our time. I'll do a short introduction, and let me just put here to start recording. And then I will pass you the floor, okay? All right, so good morning, everyone, and welcome to another webinar in our series. Today we have Dr. Barak Zackay, who is an astrophysicist at the Weizmann Institute of Science in Israel. He works with different astrophysical phenomena and invented a technique to analyze some events. And today, in his talk, he will talk about proper image subtraction and in astronomical image processing. And before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Barak, thank you very much for being with us today. The floor is yours.
Thank you for inviting me. I really appreciate the opportunity to talk. So today I'll talk about advances in astronomical image addition and subtraction. Now a little bit about me. I'm doing astrophysics, but my major tools are statistics and algorithms. And the long-term goal is to improve the state-of-the-art observing techniques in astrophysics across the board. So I'm really working on many different fields. I have some major past works. So, for example, the now called Zoggy image subtraction that is currently employed in ZTF, BlackGen, and LSST. Another example is the fast dispersion measure transform algorithm that is used for detecting fast radio bursts, that is now used in the Australian SKA Pathfinder and discovered dozens of FRBs. And in my postdoc, I worked on gravitational wave detection, specifically on the binary black hole part. And we is me with several other postdocs and Professor Matthias Alvarado. And we created an independent pipeline for the analysis of the LIGO Virgo data. And the result was really exciting. We really doubled the number of detected binary black holes. And we really were operating on the accessible to everyone LIGO Virgo data. And we also influenced the other pipelines to increase their sensitivity. And for example, in 03, several of, at least one of the pipelines added the improvements that were inspired by our improvements. And as a result, they increased their sensitivity by more than 30%. So these are my past works, and my current works is I have two works in pulsar astronomy, one in order to take radio data and detect pulsars in binary systems, that currently this is very inefficient. And I have a state-of-the-art algorithm that's in the process of being implemented in order to do this. And this algorithm is actually very broad, and I know of at least 10 applications in astrophysics alone. So this is going to be a very important work. Another algorithm is inclined to detect gamma ray pulsars. Basically, it's trying to solve the timing problems. So if you have timing of many different arrival of pulses, how do you connect all the timings of all the pulsars? So for these two things, I'm still hiring people because I can't do it alone. And other works is we are continuing the gravitational wave detection and also improving the techniques. And this I'm doing with my student Jonathan Mushkin. And there's another spot in this effort because this is a major trajectory. And I'm currently exploiting the techniques we developed for gravitational wave detection in order to improve the detection efficiency of transiting planets in the Kepler data, and specifically faint planets that are revolving in long periods, so like Earth-like planets around solar-like stars. So this is the project of my student, Orina Ivashchenko. And I have another student who is continuing a work I began at my PhD to develop a method for high contrast imaging. This work began in my PhD and was actually a continuation of the image addition work. So you will see at some point, I'll tell you how is this related. Now, why am I telling you this? Because let's focus on the talk, but I'm telling you this because I'm hiring I have many spots open. And there's also a special postdoc scholarship for Brazilian citizens. I think this program is fantastic for showing this. So let's now, without further ado, just begin with the talk. Okay. So this work was with my collaborators, then advisors, Eran Ofek and Avishai Galiam. So let's begin. So before we talk about the problem and all of it, let's just fix the notation because let's just make sure that we know what is what. So we have an image model. What does image model mean? It means that it's a way to describe to a foreign person how to create and how to simulate an image. So you take some true sky, okay? For this, you can choose whatever you want. Pick the nicest HST galaxy you can find, and then convolve it with some point spread function. So this is something about the telescope, but also about the atmosphere, as you probably all know. And add some Gaussian noise, okay? And this is the Jth image that you are measuring. So it's the mth measurement, okay? The Jth measurement, so T is the true sky, yes, okay. So let's define the problem. So what do we want when we add images? What do we really mean when we add images? So where does the addition operation came from? So we are all astronomers. We don't actually care about adding images. We care about getting astrophysical measurements done. We care about reliable detection of sources or transients. And we care about something that has no human involvement. We really don't want a person to tell me, sit down with the image and tag each source and say how much photons does it think the source gave. And what we should not care about, so let's separate the important things from the non-important things. So image quality matrix, for example, maybe those are usable if you are planning a telescope, you're doing something, in advance. But once the data is taken, we don't really care about the images and our sharpness, resolution, seeing. We just want our maximum sensitivity measurements. And whatever the way, the better the measurement, we don't care what the tool that gave us. Okay. So remember this definition, because this is very important in order not to look away and do things that really make no sense. Okay. Now the different stages, so of course, when you come to do some transient detection or image addition, there are many stages in the pipeline. This is a partial list. So for example, you have to take the images, you have to convert them to physical units, you have to find which star is which, so you have to find some astrometric solution, you have to then shift, rotate, and maybe even distort the image so that it would align with the other images you have of the same field. You then have to measure what is the current point spread function, estimate some background emission of the atmosphere or maybe even zodiac, and find the image 0 point. So convert it from current flux units to actual physical flux units. And you want to identify bad pixels and particle hits, and only after that you might want to add or subtract. And the reason I'm mentioning all of this is that, if you put into image subtraction something and you state the wrong PSF, garbage in, garbage out. And the same goes with addition. So this is very important to point out that we are talking about only this particular stage, not all the rest, and I'm not marketing any code product that does all of this, and this is somewhat in purpose. Any question? Okay. Now let's begin with addition. So the commonly used methods, I think many of them are still used, so they're not really past methods. I think they're still used. So if you have some images and you just want to sum them, so many people just say, okay, let's sum them with some weights. Okay. Some other people try to do even more than this. They try to find some kernel that if you convolve with the image and add some alphas, then it should, this is the choice you make. And this convolution, the kernel is such that the images are very similar to some reference image. So you are trying to homogenize the point spread function. This is a method that people are doing. And like as a human, I think it really makes lots of sense. But when you go by and try to derive this method, you find out that actually the optimal solution is the other way. So bear with me. But this is the real reason why I think you really should derive things from first principles whenever possible, because sometimes the human logic goes against what you really should do. Okay. So what is the problem with existing coaddition methods? So before we talk about things that relate to the images, the real problem is that there's no argumentation. You really look at the method, someone was playing with data, he was doing something, he decided to do it this way, and he puts a paper, adding images this way is, my choice. Now this, if you do it wrong, then you sometimes get reduced sensitivity. This is not to be very surprising. I think there's a question. So
yes, Rogério.
Yes, it's a very, very naive question. I'm sorry, I'm not from this field. What is wrong with just taking pixels from the image and just adding the fluxes in the pixels?
yes, so the images themselves, each image has a different point spread function. So for example, if today I'm seeing the sky better than yesterday, so today all the stars are very small, and yesterday there was very bad seeing, all the stars are very, each star takes 3 arc seconds, and today every star is half an arc second. So if you add both of them, you will get an image in the resolution of the bad image. This is what you will get. And if you actually try to measure point sources, you would see that measuring point sources from the coad would be worse than measuring images from the regular image, okay, from the individual good image. So you very easily lose sensitivity, and the effect that we are talking about is the effect of changing point spread function. So each image has a different point spread function.
Okay, now it's much clearer. Thank you very much.
Now, there were several myths in the field that for different applications you coad very differently, and there's a trade-off between the resolution and the depth. It turns out none of this is a necessity. Okay, so for example, how can images be so bad that their contribution needs to be 0? This is a sign you are doing something wrong if you have to discard data. And the coaddition methods that involve regularized deconvolution actually have some numerical instabilities. They introduce spatial correlations, and then if you come up and try to detect point sources, you get false detections, and then you raise the bar, and then so this can be really damaging to the data, to the point in which you have a survey speed that is 50% less than what you could have. And I always say that if you can spare 20% of your telescope time on being lazy, then I want to apply for 20% of your telescope time, and let's see if you like this. Now, the approach that we took is to go by the book, to really try to define the simplest statistical task, which is point source detection, find the optimal solution to this problem, then extend the solution to all tasks, then try to analyze the behavior when you add some realistic effects that were not in the original statistical model, and then see, A, are you still sensitive? And B, if you are still sensitive, does it require some small correction in order to change the reliability of the measurement? So perhaps you missed a cosmic ray, so perhaps you need to have a procedure that removes cosmic rays, for example. But there could be other effects. So for example, if there's residuals from the image alignments. So this is the approach. So optimal source detection. So the statistical task is to detect point sources. Okay, what do we want? So we want to define what two different statistical models we are trying to tell apart. So one statistical model is the image is literally 0 plus noise. And the other statistical model is that the image is, there's a single star at position P, and it appears with the point spread function of the image, and there's some Gaussian noise, okay, in both observations. And you write the Neyman-Pearson detection statistics. So this is the log likelihood ratio, okay? So basically you are taking the probability of all the images given there is a signal, and divide by the probability of all the images given that there is no signal, okay? And algebra, you get the well-known matched filtered solution. And with a sum over j, that because you have j images, and then this match filter applies j times, and these are the coefficients. Okay, and then you notice that this is actually so first of all, S is the analog of a match filter. So if I had defined a three-dimensional image, and I had a point spread function for this three-dimensional image, then this would be like the regular match filtering. So there's no surprise in this solution. But it is a little bit counterintuitive, because if you now look at what was done in, where is it? In PSF homogenization. So in PSF homogenization, each image, so you try to take some target point spread function. So if you have something very wide, you're trying to narrow it. So you have so bad images get widened by a wide PSF, and good images, sorry, the other way around. Bad images get widened by a small point spread function, small kernel, and good images are meeting kernels that are very wide. Okay, so if you look at the solution is actually the other way. Each image, so the good images meet the tiny point spread functions, while the bad images are meeting the wider point spread functions. So this is counterintuitive, apparently. And it's even better than you think. It's not only point source detection, because, for example, suppose I'm trying to detect some, I don't know, I have some cartoon model of a galaxy, and I'm trying to detect all galaxies of this cartoon model, okay? Then I want to match filter, I want to separate between these two hypotheses, and lo and behold, the shape of the thing that I'm trying to search for gets out of the summation, okay? If it gets out of the summation, this already hints that what I have here is a sufficient statistic. So what does it mean? So you have a family of things you try to model or measure, okay? And whatever it is inside this family, you can discard the data completely, and just use this sum, which is one image, in order to compute the likelihood. Okay, so you don't really need the original data anymore. Okay, and this trick works for any measurement or the decision problem of any pixelated model for the image. Okay, so this is very strong. In fact, it is so strong that maybe you can really say, okay, I really want to summarize the survey. So now we began with adding images. We didn't really know what we are doing. We started with some statistical task, and now we really have something that is adding the images, and we really understand what is the criteria. The criteria is that we will be able to make all measurements optimally precise. If this is the criteria, then what you want is to get a summary of the image, which is a sufficient statistic with respect to all possible models. Okay, and if we really want to, go extra, if we can try to even make this image a proper image. So we really want to have an image that, you can give a guy this image, and he doesn't need to know the history of how you created this image. You just give it this image, and he says, it's a fantastic image. It has a standard deviation 1 in all the pixels. You give him the physical units in which, how to interpret, flux F into physical units. You give him the image 0 point. And you also guarantee that all the pixels are independent. So he doesn't really need to know what happened to this image before. And he can create a new statistical model for this image. And lo and behold, he would compute something that is equivalent to the likelihood with all the images. He doesn't need to know there were 1,000 images before. Okay. So what are the properties of this new code? It's optimal for all decisions and measurements. It assumes known point spread functions and white Gaussian noise. These assumptions are usually correct in astronomical images. You can break them if, for example, you go to X-ray images and then the Gaussian noise goes down the drain, or if you have very, very short exposures, also the white Gaussian noise has a problem. And known PSFs, this assumption is a little bit weak because we actually don't know the PSF of the images, but I also have some derivation of what is the tolerance that you really have on knowing the PSF, and you can measure it from stars in the field, usually. Usually, it's not very hard to get to the required tolerance of the point spread function. Now, it is also a sufficient statistic. So once you have settled on all the previous stages, okay, if you have all the images and you want to report one thing to all your users, then you really don't have to report all the images. You can report only the coad. So for example, LSST is going to have several tens of petabytes of data. And in principle, you can summarize them by at least a factor 1,000 by just co-adding them with proper image addition. Okay. Now, as a bonus, you get 5 to 25% more survey speed relative to the weighted summation. And if you have done PSF homogenization before, then it's even better than this. It is numerically stable, so past methods for image addition were sometimes not numerically stable. It is local, so if your point spread function is changing with, let's say, arc minute by arc minute, okay? And the point spread functions themselves are of scales of arc seconds. So the kernels that you apply in the image addition are very local. So basically, you can handle the spatially changing point spread function. And it's indistinguishable from a regular image. You can take a software that was programmed for this survey and use for another survey. Okay, so how does it look in practice? So in practice, so here are images of those are all simulated images of a point source and a small frame. And here it's with a Gaussian PSF, and you have several different scenes. Okay, so this single star becomes broader and broader as you move from left to right. And the regular summation looks like this, and the proper coad looks like this. No surprises here, but I'll show you later that it's a little bit more sensitive. Now, when you make images, and here it's exaggerated, I put an elliptic PSF, okay, just to make the point in which if you have an elliptic PSF, so each image, so this image, for example, it knows this axis, but it doesn't know this axis, okay? And this image, it's vice versa. It knows this axis, but doesn't know this axis, okay? And the coad knows all axes, okay? So it really summarizes all information you have from all the images. And this is not shared by just adding the images. It's just not. So imagine that I put also one of these in the summation, and it would completely get smeared out. And if you take something that is even more radical, so if you take a star and you image very, very, very fast, you get speckle images, okay? If you don't know what speckle images are, it doesn't matter, okay? But this is what happened when you image like a bright star very, very fast. And it turns out that proper coaddition of speckle images can really reveal things that you wouldn't even imagine that you would know. So here there was a small companion, and you could just see it. So from this part of this project, we spawned the high contrast imaging project, which is out of topic for today, but I will be really happy to tell anyone interested. Okay, now if you try to make a cut through these images, like a horizontal cut, okay, so you would see that even when the point spread functions were Gaussian, the regular coad is more sensitive. So I aligned the images exactly the same, and I put the standard deviation outside of this region to be the same exactly for both of the images. And you have a little bit more signal in the proper coad. This is no surprise that it's a little bit, 20% more service speed is not much. This is how it looks like. if you go to the place where we sum elliptic PSFs, then the improvement begins to be much more important. And if you go to speckle images, it's a complete change of life. Okay. So what are the future prospects of image addition? So the future prospects are to deploy it, for example, in LSST. I'm not sure that I'm the person to do it, and I'm trying to get collaborators to do this, but it's still very hard, even though I think it should not have been a tough sell. It is a tough sell. And for me, the major argument to do it to LSST is not the 10% more survey speed, is actually the fact that you can really distribute summarized images of the years of data, and just give people the most of the data, and 90% of the users don't ever need to get to the original images. And another future prospect, which I actually intend to pursue, is to get what I call the super resolution, the sufficient statistic version. So if you have images that are undersampled, and this is expected for a space mission that is led by a Weizmann Institute called Ultrasat, and also a very famous other space mission like JWST. Okay. So undersampled images are appearing in astronomy in many different contexts, and being able to get the most out of them requires some thinking when you do coaddition. Okay, I'll detail it more now. Okay. So what is the sketch of this project? So you have some image formation. So the image formation, you have some electric field on the telescope, and then you conduct some Fourier transform, you get the electric field on the detector, then you do some absolute value squared, and then you convolve with the pixel response, and then you sample, you take discrete samples, and what you get is this beautiful astronomical image. Okay. Now it turns out, before it turns out, so in Fourier space, how does the image model look like? So if you take the Fourier transform of the sky, the infinite resolution Fourier transform of the sky, you then chop it to some finite resolution. For example, the aperture of the telescope gives you some boundary to the maximum spatial frequency you can measure, but sometimes the atmosphere is actually the limiting value. So whatever it is, you have some maximum spatial frequency. And then what you are doing, so the process of convolving with the pixel response is multiplying this by something. And then comes the problem of the moment where you take samples of the different pixels, and then you really have a summation of different frequencies. So all different frequencies are going to be added, and they appear here. So this piece of the Fourier transform of the image that we measure is actually the sum of these pieces in Fourier space. Okay. Good. So now we understand how the image was formed. So what's the problem with regular coaddition of these images? Is that the problem is actually in a stage that comes before coaddition. It's in the stage of shifting the images with respect to another. And this shift is going to have some subpixel component. And the subpixel component, if you look what it is doing in Fourier space, it is applying phases in Fourier space. Now, if you move exactly one pixel, then this delta x times k is periodic with this period, and then all the triangles get the same phase. And if it is a subpixel shift, then all triangles don't get the same phase. So if I want to shift this image by some subpixel shift, I come up with the question of which phase should I apply to this triangle, this poor triangle. Good. So now that we understand that it's impossible to take a single image and shift it by some subpixel measure, we understand that we really want to summarize the data. We really want to summarize all information we have on the Fourier space representation of the true sky, Okay, so the way to do it is to solve many small systems of linear equations. Okay, so I have many measurements, each one with different phases applied to the differential phases applied to the different triangles, and I'm going to solve for all the triangles using these summations. Okay, and this is a sketch. All the equations are not written yet in a paper form. Okay, but this is the current status, and this is, I think, an important problem to tackle. And this is the end of the addition part. And this is a good time to give 3 minutes for questions if someone has a very good question. This is exactly what. Okay, yes. So anybody has a question about addition?
Yes, I have a question. I was trying to do addition of some images, but I had only one star in the field because I'm dealing with very bright objects such as Jupiter, and I'm trying to get more stars in the field of view. So I have usually just one star, and I'm trying to stack this image together. I would like to have your opinion on this subject.
You need to be able to measure the point spread function. So for example, if you have a telescope that is very small, if it is just you know, some I don't know, some small telescope, you know, just add images for the beauty of imaging Jupiter, then you should try to measure the current seeing either by finding stars in the field, or maybe even, you know, just moving the telescope a little bit, taking an image and then going back to Jupiter. But once you know the point spread function, you can do proper coaddition just with this formula, nothing else.
Okay, thanks.
I think the easiest part, by the way, if you really don't look for a super scientific, super exact thing to measure out of the image, then there's a method called lucky imaging. You could probably align all the images to the same place via the limb of Jupiter, and this would already give you some improvement in the image quality. Okay, so let's move to image subtraction. So now we are already trained. We know that first we need to know what we are talking about. So you have some reference image. So it's the true sky times some PSF. And you have some new image that you have the true sky convolved with some PSF, okay? And there's no assumption on T. And there comes the question of what are we trying to do? So we're first trying to find some argumentation or reasoning to the subtraction problem. And past solutions had all of this. They had reduced sensitivity, they had false positives, they had the problem of making pixels correlated and further signal processing. The assumptions break. And the status, so the thing that led me into image processing was that in our department, my advisor was a part of PTF. Back in the day, it was called PTF. And there was an inevitable at least 1 hour latency because a student needed to go over all candidates of supernova. And this was making some science cases impossible, okay? And the methods were unstable and numerically unstable, and some of them were slow. So it really called for something that is orderly fashioned. So the most common algorithm, I think, still for image subtraction is this Allard and Lapton from '98. And you're basically trying to get the reference image to play ball with the point spread function of the new image. And you will see in a few moments that this is really ill-defined. This is not the solution, just because the real solution also contains some kernel for the new image. Okay, so we already know we should treat it from first principles. So let's state the hypothesis. So no transient means that there is an image. I don't know what it is. and it is convolved with some PSF, okay, and then some noise added. And the H1 hypothesis is the same unknown sky plus some new delta function at position Q, okay? And this is convolved with Pn, and there's an addition of a Gaussian noise, okay? Now again, you want to apply the Neyman-Pearson detection. Here you have an additional step. You have to cancel the probability of R given H1 and R given H0, just because if you look at the image model, then the image model of both H0 and H1 basically agrees on R. So this probability has to be the same. So this really cancels out. And what you have is these expressions and algebra, and you get this solution. You can trace all this algebra in the paper itself. So here let's look at what's happening to this solution. So you have the new image, and it is multiplied in Fourier space by the reverse of the kernel of the of its own point square function. So you are match filtering it, okay? And then you multiply by PR squared, and you do something symmetric to R. So you match filter R, and then you multiply by Pn squared. And then so both of them now have a PR squared, Pn squared. So if there's a point source, it cancels, right? But if there's only a point source in N, it would come up with a point squared function, which is this Pn squared, PR squared divided by this sigma squared, this. So this is the solution, and lo and behold, it is not of this form. Okay, the people were trying to stabilize this problem for 2 decades before this solution came, and found out that there's an inherent problem that the solution has an N component that is non-trivial. So why stop there? So this is transient detection, and maybe some other person is searching for something that is not a delta function. So what should I do? So maybe we should again try to get the image to be of a proper form. So this means that it has standard deviation 1 and uncorrelated noise in all the pixels, okay? And then you get this image subtraction, which now you can try to understand. So N is convolved with the point square function of R, minus R that is convolved with the point square function of N. And then you make all the different spatial frequencies have the same variance, okay? So basically the solution is simple. If I was a genius, I would have been able to think about it in advance, but I was not. And this is the solution. This is the image, the proper image subtraction. And what are the properties of it? So it's optimally sensitive with a rigorous mathematical proof. The convolution kernels are local. It is many times more sensitive than the past methods. It gives reliable significance and error bars, and this in itself increases sensitivity because you now can reduce the thresholds for detecting transients. And it has a closed form, so there's no optimization problem to solve. And it is a sufficient statistic for measuring any difference between the images. So for example, if something moved, okay, between the images, you can measure the infinitesimal movement using this. So you don't ever need the original images. You can subtract, and then you think, what do you need to measure? And it is fast and numerically stable. So in a simulation, if you just take images with Gaussian point square function, then and you make small differences between the reference and the new image, then with Allard and Lapton, if you choose as a reference the image with the better seeing, then you will get something that is okay. With Zoggy, you will get something that is always okay. Now, so this was known, and this is why Allard and Lapton worked in the past, is because people were choosing the best image as a reference, which is intuitive, but it not always works. So for example, if one of the images, if the new image specifically, has a 7/8 ellipticity. So here it's ellipticity of 1 to 2, just in order for me not to forget which of the slides has ellipticity and which does not. But if you have even ellipticity of 7/8 in the new image, if one of the axes is better than the reference, then the Allard and Lapton solution is numerically unstable, and it would never yield something that is usable. But Zoggy doesn't have this problem. The proper image subtraction doesn't have this problem, and you can detect the relevant sources that we put in. Now, if you apply it to real images, you then notice that proper image subtraction does not perform so well near bright objects, and also that sometimes you see this yin and yang, up and down subtraction residuals. And this is very easy to understand. One is that in order for the proper image subtraction statistic to be correct, the noise has to be the same for all the pixels, and this is manifestly incorrect, because if you have a bright star, then the source noise of this bright star can dominate the noise of the background, okay? So around bright stars, you need some correction. And also, if you did not perfectly align the images, then you're going to have some residuals that are just due to the fact that you did not perfectly align the images. So for example, if you have some astrometric residual at the point where you match the images, if you have some astrometric residuals, then you can really find what is the variance of each point in the image based on the astrometric residual, and so the astrometric residual and the derivative of the image. So for example, slight misalignments, if you have a big galaxy, its center would have always left some residual in image subtraction, and the reason was exactly this. There was some astrometric residual, and near the center of a galaxy there's a cusp, and something is very, very, very similar to a point source, but there's so much mass around that you did not even realize that it has a yin and yang up and down problem. So all the image subtraction algorithms prior to this had a problem that, for example, tidal disruption events that are by definition at the center of galaxies, they were basically not found because there was so much junk in the image subtraction that you just could not identify them out of all the haystack. So for example, if you have some astrometric noise, so here I put astrometric noise in the new image, then in the subtraction you'll get this. Allard and Lapton would have the same problem. And if you just try to do some point source detection, you'll have some very bad performance. And then you apply the correction to the astrometric noise. So you basically know in which pixels there could have been astrometric residuals, like this yin and yang. And lo and behold, you immediately get all your transients, and that's it, basically. So on real data, you can find some, good. So this is the image we like to show because it has a supernova. And you see the galaxy is basically out, and the S corrected has nothing to detect at the center of this galaxy, which is going to be very hard if you try any image subtraction. Good. Okay, so so I think this is just a zoom in on some other trial with a galaxy, maybe the same one. And Eran, my then advisor and now colleague, he had tried this on a supernova that he really tried to observe for many years, okay, and really try to get the photometry of the supernova to be reliable to the very end, and did some science with it. In the current status of Zogi is that it is the main subtraction engine in LSST, ZTF, and BlackGem. This is a partial list, I cannot track all of it. In at least 7 independent implementations, and I take pride in the fact that none of them is mine. And I can recommend the only code that I wrote a single line for, which is the code that is by Paul Friespike. So I helped Paul incorporate my initial implementation of Zogi into this package. And I hear from people in the field, because I'm already not in the field, but I hear from people in the field that it is now dramatically easier to detect tidal disruption events. So in the past, this was, I think it required thousands of spectra before you get a single real TDE. And now we are talking about few, like handful. And the Zwicky Transient facility, which is the continuation of PTF and then IPTF, is now has a robotic automated follow-up. So this was impossible before the proper image subtraction, and now is a reality. We really do this. They really do it automatically, and they take spectra of supernovae well into the first hour after discovery. So the future prospects are that. Flavia, you have a question?
Yes, it's about the subtraction. So the first one is a naive question, because I was reading Zog documentation, paper, everything. I quite don't understand if I want to do a photometry on the subtracted result. I want to use the D or the S image.
So you can get it out of the S, but you need to sure that you keep the physical units. So the S corrected, for example, you have to remember what is the correction in order to get back the physical units. But basically, do it from the from the D you can do everything you want. Okay, so the D is allegedly the subtraction, and you need to match filter it with the kernel of D. This gives you S by naturally, and you can track the physical units by tracking. So in the paper, there's a F, there's a flux. This flux is really tracking the physical units. I think Paul Friespike in his code has some. So so the part I really needed to help Paul in his implementation is in order to get these physical units back after all these Fourier transforms and kernels and all. But it's possible.
Okay. And the second one is about the reference image, because as you mentioned in your presentation, Allard and Lupton give this orientation, use the better seen image for a reference. Okay. This was during the default.
Yeah.
For example, if
Lupton is not whatever was before it. Allard and Lupton really made image subtraction a reality, and improvements to be made on Allard and Lupton. And indeed, if you have a reference that is much better than the new image, then mostly it will work.
Yes, of course. But for example, if you have only, let's say, 15 images that you wanted to study, you want to subtract the background from these images, but you don't have a really good reference image from this image because the object is moving slowly. You're not able to derive optimal reference image. You can use images from surveys or something else as a reference or not. It's not possible.
you can use a reference from something else. This should work. You just need to make sure that, okay, you don't have to make sure that it is advised to make sure that you use a reference of adequate depth and resolution, but whatever you feed into proper image subtraction, you get a result. If you measure the PSFs correctly, you get a result that is well defined. It will be more sensitive if the reference is better. This is true.
Okay, thank you.
Yes, so basically it's almost the last slide, so I'll just say it, and then the next slide is questions, and we can have many more. So the future prospects of image subtraction is that, so here I don't need to convince anybody, it's already like in the community. And really the front in doing image subtraction now is what are you going to do with undersampled images. So suppose I have some ultrasat mission. So the ultrasat mission, the UV satellite, it's a mission that its purpose is to detect gravitational wave counterparts. One of its main scientific goal is to detect gravitational wave counterparts. And basically it relies on having some imaging that is actually undersampled of all the sky, and then when there's a trigger by the LIGO Virgo collaboration, you go immediately to the place where the trigger was, and you take a very wide field imaging of this area of interest. And it could very well may be that you are at a very different orientation than the orientation in which you took the original reference images. And then you have to register the images. But in order to register the images, you need it to be well sampled, like Nyquist sampled. And this is not the choices that they were taking in the construction of the satellite. And we will have to find a way to make the references good enough so that any possible orientation that you take as a new image is usable. So in order to do this, you need to produce some sufficient statistic of many different orientations and have it ready in order to detect the neutron star merger that is now happening, triggered by LIGO. And also JWST would enjoy this solution, so this is very important. And this is my talk. So please ask any questions you have. I'm here for as long as you want. And if you are a student and you are very talented and you are looking to apply novel statistics and algorithms, talk to me. Thank you.
Okay, thank you very much, Barak, for the very interesting talk. We have now a little time for questions. If you joined us on YouTube, you can put your question in the comment section, and I will redirect them to Barak. If you are with us here in Zoom, please raise your hand. Yeah, you can ask it yourself. Actually, I'm start asking a question. Actually, it's connected to what Flavia was asking on using a reference image from another survey, and well, do you if you're using an image of another survey, you will have another PSF? Wouldn't it break the math behind the algorithm?
No, the algorithm, so you just need to know the PSF, okay? It's not required that the PSF would look good. So you can even take different speckled PSFs and it would work. If the images are Nyquist sampled, you can always change the pixel scale, and you can change the orientation, and you can change the position so that the image sit on top of each other, okay? And then it's just about the different PSFs. One thing that you should take into account is that if you take some reference image from a different survey, it could be, for example, that your filter, I know, your imaging R band, maybe this survey used, I don't know, R plus G or whatever, and then the sky would not be exactly the same, and you'll get many, many, many residuals. And this might kill you, and nothing can save you from this. So, you need to make sure that the filter is the same, for example. It's all about the details. But for example, it could be very interesting to take, like in purpose, two different images, one with R filter, R band filter, and one with G band filter, and use the image subtraction in order to find transients, like in terms of like, so if you have a galaxy and you want to like get the surface of the R minus G, for example, of this galaxy, then you can get something like this.
Okay, thank you. More questions?
I have a quick one. It's about the code that Paul and you made. I read in the documentation that this is still in testing. I wanna just ask you, there is still work. I mean, the code is still under development, or it's finished and that's it?
This is a question you need to ask Paul.
Okay.
As far as I know, there's a survey called BlackGem that is using this code, but I'm really not updated. So last time I saw this code, it was more than 2 years ago. So I think whatever image question you have about this code, please ask for. Actually, it's 3 years.
Okay. Thank you.
Barak, you talked about the kernel being local. How local is it when you have like a 5-minute?
So if the PSF scales is several arc seconds, the kernel is also several arc seconds. So if the changes in the PSF are on scales that are arc minutes, usually, actually even more usually, then it doesn't matter the few arc second kernels that you need to apply. The PSF is basically uniform at this scale. So look at this formula, okay? So let's go back. Okay. So here there's an effective kernel that meets n. If you just make a 2D image of this kernel, so in the paper, for example, there's a 2D image of this kernel. Okay, it is not much larger than a regular PSF. So if the point spread function is very small compared to the scale in which the point spread function is changing, then you can use the approximation that the point spread function is constant for a patch. Let's say, I don't know, 100 pixel by 100 pixel patch, okay? And then you can apply whatever you want over there. And in the next patch, you're allowed to measure it, to know from an external source, whatever point spread function you want.
Okay, but how do we deal with optical distortion over the image?
What? Sorry?
Optical distortion.
Optical distortion. So
yeah, sometimes you have a little distortion because of the optics of the system. This is a completely different problem, probably.
So optical distortion. So as I said, where is it? At some point I had a list. Yes. So in the image alignment, you need to also remove the distortion and resample, right? So
okay.
if you have two images and you have some astrometric solution, okay, then you know in the coordinates of this image, what is the coordinate, like a particular XY in this image corresponds to the particular XY in the other image. Okay? And once you have this map, then locally there's going to be a linear map and you can just take the relevant pixels and rotate them and resample them to have the exact same scale, and then you can move forward.
Okay. Well, thank you very much.
Thank you.
Are there more questions? Yes. Let's just wait. If there is someone with a last question. Well, okay. If there are no more questions, we will now wrap this up. This presentation will be available on our website and on the LIneA's YouTube channel. And for the next week's webinar, we will have Dr. Robert Morgan. He's from, he works in DES, and we'll be talking about novel deep learning detection strategies for strongly lensed transients. Thank you very much. Thank you everyone for attending, and a special thanks for Barak for being with us today. Thank you, Barak.
Thank you, Rodrigo and Flavia, for inviting me. Thank you.
Yes, and
Thank you.
Thank you everyone, and everyone have a great day. Stay safe, and I hope to see you all again next week. Bye-bye.
Bye.